Just hold on. My name is Jo Clark and I will be hosting the 3 webinars this week. I'm just going to give a brief introduction to the event and then I will hand over to our first speakers. So we believe that a whole system approach to materials is essential to accelerating decarbonisation to net zero. And this runs from manufacture of the fundamental materials through to the technologies and the way they are used and to the eventual end of life. And steel, which you will see heavily featured in our series, is a perfect example of the decarbonisation and circularity of materials that is possible. So the projects you will hear from are well positioned to work across that system, and they are all coming together as a project called Switch Connect to make our research more accessible. This series of 30-minute webinars presents 3 examples from our research across the system. Firstly, today you will hear about the fundamentals of steel manufacture. Secondly, the development and use of new solar technologies. And then on Thursday, finally, to planning for end of their useful life. Each webinar will include a short presentation and then there will be an opportunity for questions afterwards. So do please type any questions you have in the Q&A box. We can pick these up at the end. So without further ado, I will now hand over to Professor Cameron Pleydell-Pearce, Professor Peter Styring and Dr. Enrico Andreoli from Sheffield and Swansea Universities to learn more about Sustain and their work on the capture and use of carbon dioxide emissions from the steel making process. Over to you. Thank you.
Hello there. So next slide, please, Lydia. I'm Cameron Pleydell-Pearce and I'm the Deputy Director of the Sustain Hub. Everybody needs a good acronym. So Sustain stands for Strategic University Steel Technology and Innovation Network, and we do place quite a lot of weight on the network element of that. We're quite an open and collaborative bunch of people. Sustain is part of a suite of one of the largest critical mass activities that EPSRC fund. They're called manufacturing hubs, and they provide a stable source of funding over 7 years to develop critical mass supporting key areas in the areas of manufacturing to support the wider UK economy. First of all, I just wanted to give you an idea of what Sustain looks like at a glance, and you can see the URL up there so you can get much more information on the project from that. The hub sits at Swansea, it's led at Swansea with the 2 initial spokes at Warwick University and Sheffield University. You'll be hearing from colleagues from Sheffield University later. We're driven by 2 grand challenge research areas. That's what the GCRA bit stands for. The first one is around net zero steel making, and the second one is around smart steel processing, with the idea that the first one gives us long-term sustainability, and the second one gives the UK competitiveness to support its wider economy. And then the idea is that we use those 2 grand challenges to drive our research ambitions, and then we hopefully deliver back to the company partners informed investment decisions, capacity for research, and also future skills for the workforce to deliver novel technologies for decarbonisation. We link with innovation partners across the UK. You can see some of them mentioned there. And then we have some key vision and opportunities that we want to address as part of the programme. You can see that we've also engaged since we started with a wider range of other partners across the UK. So this isn't a closed shop activity. And we've since funded work with Durham University, Cardiff University and UCL in a variety of different areas. And we work closely with other critical mass activities like the TFI Network Plus, for example, looking at transforming the foundation industries and cross-foundation industry collaboration to try and build the community together through a series of events, more and more in person as we run into, come away from COVID. Lydia, next slide, please. So just a quick comment on why we're doing it. So just to consider the UK in a global context, despite macroeconomic turbulence, the use of steel continues to increase at an almost exponential rate. And if you look at the IEA forecast, they say that that's probably going to increase to about 2.2 billion tonnes in their sustainable development scenario through to 2050. Unfortunately, if you look at what's happening to scrap availability, then you've got about 1.3 billion tonnes of that available. So if you look at what we consider to be the future demand under current projections, we're not going to have enough material in end of life to simply recycle our way out of the problem. And this presents a massive challenge for the steel industry, which requires a holistic approach, looking at things like carbon capture and utilisation from some of the existing processes potentially to deliver sustainability, both in terms of environmental capabilities, but also in terms of our moral obligations, because we have to consider that the availability of scrap is not geographically uniform. And actually, many of the countries that are going to be most adversely affected by climate change in terms of weather are also those ones that are developing countries and need the most infrastructure to be supported by steel as a key material. In the UK, we're in a much better position than this. We've got an abundance of domestic scrap, and that gives us some opportunities, but that isn't a market of ever reducing availability. And you will see steel scrap becoming an increasingly important commodity. So that's one element of how we're trying to approach this. Lydia, next slide, please. And of course, we also have to focus on the products. So what is it that we're delivering to the wider society? And you'll see the use of some of these products in some of the forthcoming elements of this webinar series in the construction sector. It's likely that we are going to continue to use steel because if you look at iron as an element, it's inherently low carbon footprint compared to almost any other competitor engineering material. But it's unlikely that those materials are going to be the same. Lydia, can you just click on one, please? So what's happened in the past is that we've created increasingly complex grades, and that's actually given us less control over the products, or it means our processing becomes more stringent. I think in the future, we're going to need to deliver more robust products through differentiated processes and novel heating technologies that don't involve burning gas. And there's one illustrated down there, that's near infrared heating. And also we're going to need to work harder to use the models that control these processes to develop more detailed information on that material as it goes through the supply chain so that we can manage it all the way through the supply chain and ensure that we maximize circularity for this material and reduce the overall carbon footprint of steel use, not just steel production. So just one more slide, I think, Lydia. And this is, so just to point out, this is something that's already happening. So in terms of the research, you can go on, Lydia, sorry. Thank you. In terms of the research, I mentioned the Grand Challenge research areas. That's split by 5 themes. And then beneath that, there are a large amount of tasks. And you only have time to hear about one of those today. But we also have work covering that wider remit of sustain through digitization, resource efficiency, thermal efficiency, and how we look at tackling novel heating technologies, and how we both measure the product quality and look at novel methods for developing new products. So one more click, I think, Lydia. Now you're going to hear a bit more about emissions control from Peter and Enrico, which is just one element of this program, but a particularly important one in the context that I've just presented. Thank you. I think it's over to Peter now.
Okay, thanks, Cameron. So can we have the next slide, please? Right, so I'm from the University of Sheffield, and we're looking at carbon capture and utilisation. We're not looking at storage, although this technology can be used for storage. In terms of net zero, this is something I mentioned yesterday. We have something we refer to as the unicorn in the room. We have net zero technology, which is an aspiration which, if we're looking at CCS, will only be a net 30 technology, not net zero, because you can't create energy from nowhere. You need energy to power the system. So what we've devised under this program is something called Fluorifin, or HIPSA XL. It was the old name for it. This is a pressure swing adsorption system. So what we need to do is go away from the conventional. And Cam mentioned near infrared heating as a possible source. That's a step change away from what we have. I don't know if you can see in my room, but on the wall is a far infrared heater. We're getting rid of the gas power in the room because it's an evolution of technology. So if we concentrate on amine technology from temperature swing adsorption, we will never get to net zero. It's a simple fact. So we're looking at this high pressure system, which we now call Fluorifin. And this is a pressure swing system, which is useful over a whole range of different concentrations. Why do we use steel gas? Well, if you look at that graph there, if we start off at the lowest concentration, you have direct air capture. Yes, we can do that with this system, but it's going to cost. HVAC air conditioning systems have a concentrated source of CO2. Again, it's going to cost. Combined heat and power is around 9–10%, and that's the same for gas-powered power stations. Steel has the higher of the concentrations, so it's an obvious low-hanging fruit to look at. So we're targeting steel gases as the way of taking around 30% concentration carbon dioxide, up to 100% in a single step, with an energy cost which is something like 25% of that you get from temperature swing adsorption with amines. It's got a lower footprint, it's cheaper to manufacture, it's got everything going for it, and we now need to prove that it works. So it's now going out to the steel industries, and we're going to hook it up to the emission stacks and just prove that it's a viable technology. Okay, next slide, please. The problem is, what do we do with the CO2? It's difficult to store it, and projections of when there'll be a viable technology range from 10 to 15 years in the future. If we want to act now, we need to do something quickly. And I've been talking to a company who say we can get this technology in the market in 2 years' time. That's what we're looking at. We're looking at acting now, not waiting and just pushing the deadline back and back. Because remember, net zero is really an ambition, and we need to make it a reality through action. So what are we trying to do? Well, the Sustain project is part of this, and the Circular Economy Centre that we run, Circular Chem, is also part of it, and we're hoping to work together on this. What we're trying to do is not decarbonize because we need carbon. We're trying to defossilize because we don't need fossil carbon. So the idea is to eliminate fossil carbon from the supply chain and produce what are known as e-chemicals instead. So harnessing the electricity from renewables or nuclear and putting them into carbon dioxide to convert them into things like the front end of the supply chain, really. If you look at a petrochemical supply chain, instead of having fossil fuel there, you've got carbon dioxide and you've got water. You need catalysis, you need renewable electricity, but once you've got that, you can start to make methanol, alkenes, methane, alkanes. You can even make carbon fiber and graphene, and some colleagues in the States have already done that. Once you've got those, you can go to higher chemicals, and you start the proliferation of the different chemicals you can produce along the supply chain. Ethene is one of the primary products for the supply chain. You can make ethylene oxide from there, you can make alkanes, polyalkenes, you can make synthetic jet fuel. So the possibility is limitless. Within the next couple of months, we hope to be on the second rung of that supply chain and be able to produce some fuels that can be used on site at the steel companies. So with that, I will hand over to Enrico.
Oh, thank you, Peter. Next slide, please. Thank you, Lydia. So I'm Enrico. I work with Peter on task 1, emission control of Sustain. And as Peter highlighted before, we work on carbon capture and utilization. Today, since we have just a few minutes to talk to you, I decided to focus on utilization. This is a little bit of a pictorial form of Peter's slide. I'm a chemist, so I love molecules, but I thought if in our audience we have people more engaged with pictures, here they are. So on the left-hand side, you see what could represent a process. Those are 2 fans of a direct air capture unit. In this case, however, we want to capture CO2 from steel making, and we heard from Peter the reason. It's more concentrate CO2 in those process gases than in air. And then what do we do with CO2? With CO2, we'll devise processes. We are actually developing these processes as a part of Sustain to create a new way of a defossilized, I agree, that's the right word to use, chemical industry. To generate all those products that we consider as granted, right? We go and get drugs when we need so pharmaceuticals, when we have the flu, or we find polymers everywhere. I know plastic is a bit of contentious topic, but it's part of our lives. And then fertilizer. These are just 3 examples. Next slide, please. So again, a few other pictures here. We mentioned chemicals, e-chemicals. So what we need for that is renewable energy on the left-hand side in the bottom, like energy generated, electricity generated using wind turbines. And what we do as a part of Sustain is to take CO2 concentrated, recovered from emissions or process gases of steel making, And then those electrons with CO2 and water, with the devices we are developing within Sustain and the institute I belong to, the Energy Safety Research Institute, ESRI, we are developing systems, so devices, electrodes, and catalysts to do this transformation. This is a very high-level description. If you want to know more about the details of the technical aspects and scientific aspects, just get in contact with us. Next slide, please. Thank you. So how do we do this? We start from first principles. So we really do those calculations to determine how a specific catalyst, in this case, the orange balls you see on the left-hand side are copper atoms. And we use this copper modified with several additives to facilitate carbon dioxide conversion to the products that Peter mentioned before, in this case, particularly ethane or ethylene. From there, after we understand, or we try to understand and find a way to facilitate this conversion, we make the actual catalysts. You can see them on the right-hand side on the top corner. These are micro nanostructures made of copper. Later on, we transfer those on substrates on the left-hand side corner on what we call in our area a gas diffusion electrode. So that's an electrode where water, CO2, and electrons meet to become what we consider an added value product. They are called gas diffusion because gas diffused through it. You will see later on a short video of the operation of the GDE. And then in the lab, we have the whole equipment to run an electrochemical CO2 conversion cell using GDEs. Obviously, as you can see, all these fits on a benchtop of a laboratory. However, in our approach, we have scalability in mind. What does it mean? It means that we are not fancying to develop very expensive and complicated solutions. We try to keep our approach the simplest possible and scalable, both in terms of technical aspects and cost. Next slide, please. Here you see just a couple of examples of what we did in the lab. But as I said, we are looking at the device and the system overall operation. You can see a couple of micro nanostructure on the left-hand side on the top. So from nanoneedles to microcubes. Why these different? Depending on the structure, you determine the fate of the CO2. So the CO2 likes to become ethylene on some structures and something else on other structures. So that's one of the complicated aspect, complex aspect of this process. We then take those structures and put them on a copper mesh. So we make what is called a self-supported GDE copper electrode. We make it then hydrophobic. You see this drop that is taken and put back on the top of the GDE. And on the right-hand side, a video showing gas evolving on the GDE on the left-hand side. Probably the quality is not the best, but you should see some fizzing coming during the operation. So this is a very simple description of what we do. I would be very happy to talk to you more if you are interested. The goal, as I said before, within Sustain and the effort within Sustain is to take this technology not at the scale you see, but on a larger scale. But the state of the art currently of this gas electrolyte-based CO2 electrolyzer is such that studies are still essential at this level of technology and readiness. And I think this is the end of my part. So I pass it back to Joe, correct?
Yep. Thank you. Thanks all. I think despite them being fairly short presentations, you've given us a really good insight into your fascinating work. It sounds very interesting. I can't see any questions in the Q&A box at the moment, but I did have one question, I think, for Cameron. You mentioned that that you were working with lots of different companies and organizations and more than when you started out. I just wondered what opportunities there are for others to engage in the programme, for those who are currently not involved but might want to get involved.
Thank you, Joe. So there is, in terms from the company perspective, we're basically always looking for more companies. We're definitely, I mentioned explicitly mentioned quite a lot of stuff around products and how steel as a product can also help with the decarbonisation ambitions of the customers. And I think that involves a lot of stakeholders through the whole supply chain. So some of those upstream of the steel companies, and we work with those, some of the steel technology providers to the steel companies, but of course, most importantly, the customers and ultimately the citizens who use the material as well. We want all of those groups to become stakeholders in the program, and we definitely have a renewed focus on that. It's helpful in a way from that perspective that actually a lot of the companies are now asking us to help them with their embedded carbon in the materials that they use to generate the products and services that they want to deliver. And I think the steel industry has an important role in that. And then from the academic perspective, so we're always open to new partners in that sense. And then from an academic perspective, we run calls ourselves to fund people to join the partnership. That's what we did with the universities I mentioned earlier on, so Cardiff, Durham and UCL. And at the moment, we actually have in fact, Lydia, do we have a slide? Is there a slide? Ah, good. So there's we actually have a helpful there. We actually have a call open at the moment. So we opened a call on the 6th of June, and it closes on the 29th of July. So there's plenty of time to apply. They're relatively short applications, and these are for small pots of funds to explore ideas that are novel and complementary to the work that's already going on in the programme. We've already run an introductory event, but we have a sandpit event next week, and we would encourage people to register and attend for that, where we'll be able to introduce you to industrial contacts and facilitate the development of your proposals. And that would be a good opportunity for you to engage with the programme. We'd really welcome that.
That sounds great. Thank you. Right, we have a question in the chat. Okay, somebody has said we are all understanding the essence of circular economy and sustainable energy. However, we're still dependent on non-renewable resources. How could we achieve this in full? I suppose a full switch to renewables. Whether that's possible, I don't know who wants to take that question.
Do you want me to start?
Yes, please.
Okay, so what we have to remember is this is not a switch, it's a transition. This is something that will not happen overnight. This is something that we need the public to buy into, we need governments to buy into, we need industry to buy into. And it's a multi-agency approach. We are chemists, we are chemical engineers, but I also have an associate fellowship in politics. So we're talking to government to try and change the mood, try and change the agenda. It is going to be a slow transition, but it's something that we have to do. And a lot of it is behavioural change as well. I noticed when I was driving back from Warwick yesterday, a lot of people were driving a lot slower than usual. And that is an enforced behavioural change because of the cost of fuel. And I saw my fuel consumption go to record levels of good consumption. So it is a transition. And we need to just embrace that transition.
Yeah, thank you. I think that's true. I think everyone's realised they've got to do everything they can. I was hearing about people turning off their air conditioning in cars and everything just to try and save fuel. I think we're all aware of that. I wondered as well if you're actually looking at any carbon storage of the carbon capture, or is it just utilisation? Because of course storage will have a massive role to play, won't it? Is that one for Enrico, maybe?
Yeah, particularly within Sustain, we are not focusing on storage. Utilization, it's essential in terms of, as we said before, the fossilizing the chemical industry. As you said, carbon storage, however, it's also essential since we are talking about an enormous amount. We're talking about 1,000 gigatons of CO2, which potentially, if we were, let's say, able to have enough energy, enough chemical plants, we would make so much product that we have then to store the product. So probably connecting with the concept of transition that Peter highlighted. Yes, we have to look at these in terms of storage and utilization as two solutions that are going hand in hand rather than in a competitive way, because we both need each other. Yeah. And probably something I want to say. I see other questions and the time is limited. What I want to highlight is I had a conversation recently with a group within the university about skills. And being part of chemical engineering, there was a discussion of how oil and gas and how bad all that is, because a good part of the issue comes from there also. However, in this transition, those skills will be essential. So why am I talking about this? I read in this question, yeah, we need, we are still dependent on non-renewable resources, but we still need those skills. And those skills will help us during the transition. We don't have to look to the past as something that we have to scrap entirely.
Yeah, quite.
Yeah.
Just to add to that, there's an excellent document from the European Commission called A Clean Planet for All. And that basically sets out the agenda for the next 50 years. And CCS and CCU are hand in hand. Most of it goes to CCU through synthetic transport fuels, because we need to fly planes, sail ships, etc. So it's called A Clean Planet for All from the European Union.
Yeah, sounds great. Thank you. And then there's just one final question I think we've got time for. Are there any fossil fuel companies involved in Sustain?
I can address that one pretty briefly. No.
That's a good answer.
I think we are looking to build relationships with the chemical sector. I'm not an expert in that sector, so I don't know where people self-identify within that realm. But we're definitely looking at, as Peter has already highlighted, providing a bedrock on which we can supply alternative sources of fuels that will have a net zero credentials. And just to build on that, and if a wider company wants to take an interest in that as opposed to pumping oil out of the ground, then of course we'd be happy to engage with that, as long as it's heading in that positive direction. I think just to build on the points that have already been made on energy, there is a easy option, which is just to say we're going to electrify ourselves out of this. I think this is what the question is getting at, without necessarily looking at what the carbon load is on the grid. And there's further presentations coming up in this series which will demonstrate how we might be able to tackle that with active buildings like the one behind you, Jo.
Yeah.
But there are also other options around resource efficiency and circular economy that will help us to do that. We've presented one today on chemicals, but there are also examples of how we can do that with critical elements that exist within the large volumes of material that steel companies have to produce. And there are also the byproducts that come from steelmaking processes that are absolutely critical in the decarbonisation of other very difficult sectors to decarbonise, of critical materials for our development, like concrete. And I think without having all of these sectors working in harmony, we won't be able to realise all these benefits and reduce our reliance on the energy or the carbon intensity of the grid, which is not going to be an effective way of dealing with this in the very short term.
Yeah,
so that's why Sustain's taking a holistic approach to this in the research programme that I presented earlier on.
Yeah, no, thanks. That's really, really good point, really clear. I think we've got time for this one last question. Is nuclear energy is a great resource of energy. What are the disadvantages of it? I think perhaps you mean the demerit of it. I think.
Okay. So the problem with I'm not an expert in fusion. The problem with fission is of course the longevity of the activity of the materials that you produce, which is not so much a problem that you do to a degree, but it's not so much a problem that you have with fission. The problem with fusion, of course, is that people say glibly that it's always 40 years away. However, I would say on that there is significant opportunity, and also just to quickly plug the fact that steel is actually a critical material for that. So we work closely with the UK AEA, the Atomic Energy Authority, on their fusion program to help develop and deliver future steels for fusion. We recently funded an early career researcher to work with the UK AEA on that. And actually steel is probably one of the critical materials in delivering a future clean nuclear supply of electricity, which is going to be part of the mix. As Peter said, it's all going to be part of the mix.
Yeah.
So
I think one of the ways forward is, and this is a conflict of terminology, SMR for SMR. So small modular reactors for steam methane reformation, producing hydrogen, for example, using localized small modular reactors. I think that is the way forward. And in terms of fusion, Europe is pressing ahead with the ITER program, and I think there's a follow-on from that. I've seen bits of it in operation, and it's probably 20 years away rather than 40 years away. But the big problem is time. We can't do it tomorrow.
Yeah, I think thanks to all the speakers. I think what's come across in this is that it's a holistic approach, and we need a lot of different solutions. There's not one solution to decarbonize, is there? So yeah, thanks to all the speakers, and thank you to the audience and for the interesting questions that we've had today. Hopefully see some of you on our other webinars tomorrow and Thursday. Thanks all.
Bye.
Bye.
Thanks.
Bye-bye.